Hello and welcome. In this video, we're going to take a look at the notes for AP Physics 1, Newton's Laws. Remember to pause or rewind the video as needed. Let's begin. Section 2.1, Describing and Representing Interactions. Explain what gravity actually is. Does gravity pull down on you? Gravity is the interaction between two objects. Earth's gravity is an attractive force that pulls every object towards the center of the Earth. Write a brief paragraph summarizing the hypothesis, experiment, and conclusion about how air exerts a force on the ball. So as a ball flies and falls down through the air, we have air resistance acting upward on the ball. At least that is the hypothesis anyway. We could say something to the effect of, the hypothesis is that the air exerts a downward force on the ball. To test this, attach a ball to a spring. We notice how far the spring stretches and measure it. We place that ball and the spring inside a large jar and connect it to a vacuum pump and pump the air out of the jar, creating a vacuum. When the air is removed, the spring stretches farther. The conclusion is that the air must have been exerting a small upward force on the ball. My apologies, that's a typo right here. That should be upward. Briefly summarize how to make a free body diagram. Say everything that is important about a free body diagram in as few words and sentences as possible. First, we sketch the situation, we draw a picture of the object, and identify all forces acting on the object. Then to draw the free body diagram, we essentially free the body, and we have a dot that represents the center of mass of the object. And in that dot, we're going to draw arrows representing the interactive external forces acting on the object. Label all forces with the symbols and sometimes subscripts as needed. What is a normal force? A normal force is a perpendicular force from the surface acting onto the object. The word normal means perpendicular. So to have a normal force, you have to have a surface, but more importantly, we have to be acting perpendicularly from that surface. Section 2.2, Adding and Measuring Forces. What does it mean to say that force is a vector? Forces, being vectors, have magnitude, which is an amount of force, and they point in a particular direction. Let's spend a second taking a look at how to find the net force on the following situations. To find net force, we're going to essentially take the bigger force minus the smaller force. The bigger force is called the causing force because it causes acceleration. The smaller force, well, that's called the opposing force because that resists, or as the name suggests, opposes acceleration. So net force is this variable sigma f. Sigma means, that's the Greek letter sigma, and it stands for sum, adding, the sum of force. The sum of force is another way to say net force. Well, it's going to be your causing force minus your opposing force. So here we have two forces acting on it, 20 newtons upward and 15 newtons downwards. Let's draw a picture of that. We have a force that's going 20 newtons upward and 15 newtons downward. Since they're going in opposite directions, this is very easy to apply. And the net force is going to be 20 newtons minus 15 newtons, which equals 5 newtons. Now, since the answer is in the direction of the larger force going upward, that means the net force is also going upward. Something to keep in mind, and it's going to show up later and fairly continuously throughout this unit, Net forces, according to Newton's second law, cause a mass to accelerate. Net forces cause a mass to accelerate. Well, the direction of the net force, that is the same direction as acceleration. Acceleration always points the way the net force is going. Next example. What is the net force on an object that has two forces acting on it? 20 newtons to the right and 15 newtons to the right. So in other words, we have this dot and we have two forces, 20 newtons to the right and 15 newtons to the right. So net force would be causing force minus opposing force. And, well, guess what, guys? You don't have any opposing forces. You essentially have two causing forces because both of them cause the acceleration that will be pointing to the right. So in this case, since the forces are pointing the same way, right, we add them together. Opposite ways we subtract, same ways we add. And we get 35 newtons of force pointing to the right. Does an object, quote, have force, unquote? Is force something you or an object can possess? Now, when it says explain, use the tip box, well, the tip box is something that is inside the electronic textbook in section 2.2. Okay, but you can follow along with me now here and get the same result. Does an object have force? No, objects do not have forces. They do not contain forces. Forces do not reside inside of objects. Forces represent the interaction between two objects or more than two objects. For simplicity, we will just really account for two objects. The direction of the forces between those two objects and the magnitude, the amount of forces between those two objects. But it does not reside in any single object. Okay, let's skip the example for now as we will do that together in class. Section 2.3. What quantity has the same direction as force? What does force actually do? Write a brief paragraph to explain the answers to the question. Cite evidence from experiment tables in your electronic textbook. Acceleration, ladies and gentlemen, is what points the same way as a net force. Net force is caused in objects, causes objects to change velocity or to accelerate. If the net force points in the same direction as velocity, the object speeds up. If the net force points opposite the object's velocity, the object must be slowing down. It is if the net force is zero, meaning forces point in opposite directions are balanced, then the objects must be continuing to move with no change in velocity or move in a constant velocity. So again, our Newton's second law tells us that a net force causes a mass to accelerate. And here's what we're trying to say. The direction of the net force is the same direction as the acceleration. They point the same way. Section 2.4, reasoning without mathematical equations. An object is moving upward, has a greater downward force than an upward force. What is the object doing? Use conceptual exercise 2.3 to answer this question. Okay, so let's draw a picture of this this situation. So in exercise 2.3, we've got an elevator. The forces of which, and we're talking about the person on the elevator. So not the forces acting on the elevator, but the force acting on the person inside the elevator, would be their weight and the normal force inside acting on their feet. Now, it says the object is moving upward, so the velocity is upward. Okay, and we are told that we have a greater downward force than upward force. So the weight is greater than the normal force. Weight is greater than the normal force. So what that means is the net force has to be in the downward direction if this force is greater than that force. And if the net force is in the downward direction, that means the acceleration is also in the downward direction. So what does this mean? What is the object doing? The object, which in conceptual exercise 2.3 is an elevator, is moving upward, as we were told, but slowing down. Remember, when objects slow down, velocity and acceleration point in opposite directions. When objects speed up, acceleration and velocity point in the same direction. Sorry, moving upward. Section 2.5, inertial reference frames and Newton's first law. What is an inertial reference frame? An inertial reference frame is one in which the observations that are made in that the net force and the acceleration of the object are consistent in direction. So, in other words, the acceleration always points the way the net force is going. Now, this is true in certain situations. Let me give you an example. If you are looking at, let's say, a person in a car, okay, and you are outside the car observing the person inside the car, and the car is moving, and the brakes all of a sudden slam on, and the person goes flying forward right into the dashboard. Well, the person accelerated forward, but the problem is nothing actually pushed the person forward. There was no, so from the frame of reference of a person inside the car, that would be referred to as a non-inertial reference frame because it's inconsistent. There's no net force really pointing the same way as the acceleration the person's experiencing. However, from the point of view of the outside observer, the car and the person inside the car are really one. They're really operating under the same constraints. So the friction of the tires, right, slow down the car, and that's what we experience as a net force causing the acceleration or rather deceleration rapidly. So from the perspective of a person outside the car, their point of view would be an inertial reference frame. So inertial reference frame, again, it's one in which the net force, the observations made about the net force and the observations made about the acceleration, they're consistent with each other because acceleration and net force should always be going the same way. State Newton's first law. Newton's first law tells us that objects will continue moving with a constant velocity when the net force acting on the object is zero. In other words, forces acting on it in opposite directions are balanced. What is mass? What is inertia? Briefly explain how these concepts are connected. Mass is the amount of matter of an object. Inertia is the resistance to a change in velocity. Inertia is directly related to mass. It's not equal to mass, but it's related to it, meaning large masses have large resistance to change in velocities. Small masses have very little resistance to change in velocities. And think of it this way. If you have a big truck versus a small sports car is easier to change its velocity. It's easier to accelerate. It's easier to decelerate. A bigger truck is harder to get up to speed. It's harder to slow down once it's in motion. Section 2.7, Gravitational Force Law. What is the relationship between weight, the gravitational force on an object, and the object's mass? State the relationship as an equation and in words. Well, the gravitational force is the product of the mass and the acceleration due to gravity. Now, sometimes the acceleration due to gravity can also be a measure of the gravitational field strength. Say, well, what is a gravitational field? Well, gravitational field represents invisible lines of force acting on each mass. And so the gravitational field describes the strength of the gravitational force. The stronger the field, the stronger the force. The equation for it, well, remember we could use F sub G or F sub W for the force of the weight, or just W. All of those are acceptable variables for weight. I usually go back and forth between these two. So F sub G equals mg, right? Or you could write weight equals mg. I'll write this one quite often. Now for G, remember G is a 9.8 meters per second squared, but you want to basically round it up to 10. 9.8 for labs. Okay, 10 for everything else. Are mass and weight the same thing? Are they measured in the same units? Are they directly or inversely proportional? Write a paragraph that explains the answers to these questions. Well, mass and weight are not the same thing. Mass is a measure of the quantity of matter. For all intents and purposes, mass is basically how big the object is, where weight is a measure of the Earth's gravitational attraction to an object. Mass is measured in kilograms, while weight, a force, is measured in newtons. You could say that they are directly related to each other, meaning the greater the mass, the greater the weight. Section 3.4, friction. Explain the circumstances under which static friction acts. Well, static friction acts to prevent motion. Static friction is the type of friction that holds or prevents an object from sliding or skidding on a rough surface. What does it mean that the static friction has a maximum value? Describe a situation in which static friction is less than the maximum value. What would happen? Describe a situation when the force is greater than the static friction's maximum value applied to the object. What would happen? Well, if force is applied to an object and the object does not move, that means static friction is preventing the motion. Now, there has to be a minimum amount of force needed to overcome this static friction, okay? When this happens, the object slips and moves on. So let's talk about the scenarios that they asked us. Describe a situation in which static friction is less. Well, very simple. Let's say we push a box, and it does not move. Then push harder, and it still does not move. Right? What is this telling us? This is telling us that there are several lesser values of static friction leading up to a maximum value, right? And all of them are balanced with the amount of force. So if I'm pushing the box, the static friction balances the amount of force that I'm pushing. If I push harder, static friction acts at a greater magnitude until we reach a maximum value. So now describe a situation in which the force is greater. Well, when we push the box hard enough it slips and begins to move. So what we've done is we've pushed with a force that is just a little bit, it's at least the value of the maximum amount of static friction. What does the coefficient of static friction depend on? Well, the coefficient of static friction depends on what the two surfaces that are interacting. So for instance, maybe it is wood on wood, or the rubber tires on concrete, or various. There's a lot of different examples of different surfaces that interact, but the coefficient of friction completely depends on what those surfaces are. What is the equation for static friction? Well, the equation for static friction is F of S is less than or equal to mu sub S times the normal force. Now, this right here, that is an inequality that basically means it's going to be all static friction values less than or equal to a certain value. In other words, up to a maximum value. So what does that mean? It means at most, right? That means at most. So we're talking about a maximum, all the static friction values that lead up to a maximum. Now, usually, however, we will use F of S is equal to mu sub S times the normal force. So it's less than or equal to. Most of the time we just apply the equal to, because really we're concerned with using the maximum value of static friction. But please note that any value of static friction that's less than the maximum, right, could also apply to. Explain the circumstances under which kinetic friction acts. Well, kinetic friction acts to oppose the motion of the object sliding along a rough surface. So if that box we mentioned in the previous example is pushed to the right, kinetic friction, moves to the left, right? Friction opposes motion. The equation for kinetic friction is F sub k equals mu times the normal force. The basic equation for friction is really easy to remember. Friction is fun. Does everybody see how the mu kind of looks like a U? Friction is fun. Now, we just have slight variations in terms of the subscripts we use, okay? But it's essentially the same equation. Skip the review section here and move on to this case right here. A person pushes the box as shown. The box slides across the rough floor. The dot on the far right, draw the forces acting on the block as it slides. There are 4 forces. Okay, so if we're pushing, we have a force, applied force. You'll have friction. You'll have the weight going down, and you'll have the normal force going up. So those are the 4 forces they're talking about. Now just draw them from a central dot. Now, here's what we don't know. I'm going to draw the forces a certain way. I'm going to draw F going this way. I'm going to draw friction is fun going that way. I'm going to draw weight equals mg going that way, and I'm going to draw normal force going that way. Okay. Now, we don't know if those 2 forces are balanced or unbalanced. In fact, that's what these cases are going to allow us to examine, and we're going to take a look at them one at a time. However, those forces are going to be the same forces in all 3 examples. Okay, so here's what we're going to do. We're going to rank the forces from strongest to weakest in the following case. Put an equal sign in between equal strength forces, and put a greater than sign between unequal strength forces. Case 1. The student pushes the box so that the box speeds up. Now, if it speeds up, velocity and acceleration go the same way, right? So if we're pushing the box to the right, acceleration goes to the right. So if we redraw our force diagram, we have normal force, we have weight equals mg, we have F, and we have a smaller friction force. Now, you'll notice something about the detail of how I drew this. I drew friction smaller than I drew the normal force, and here's why. Friction is equal to mu times the normal force, and mu is going to be a decimal that's less than 1. So a decimal less than 1 times any normal force, what that means is friction will always be less than normal force, 100% of the time. So I draw the friction vector shorter than normal force 100% of the time. Now you'll notice I drew the applied force longer than friction because I was told that the object is speeding up. And since the box is being pushed this way, the acceleration is also going that way. Therefore, the net force it has to be going that way, which means the applied force needs to be greater than friction in order for the net force to be sliding to the right as well. Okay, so now let's examine how this would look. Well, weight and normal force are equal, so weight is equal to normal force. Okay, and why am I putting them first? They're longer vectors. They're going to be greater than friction, and friction is going to be slightly less. They're going to be greater than friction and applied force. Now, between friction and applied force is greater than friction, so I could write it in that order. But those two should be equal. In case 2, the object is slowing down. So go and draw the free body diagram again. Again, we have normal force, and we have weight. Okay, and again, they're equal. But this time, if the object is slowing down, my velocity goes one way, my acceleration goes the other way, my net force has to go that way. That means friction has to be the causing force of the deceleration, and the applied force is going to be the smaller opposing force. Probably shouldn't draw it that long, like that. Something like that would be a pretty accurate picture. So those are greater than friction, which is now greater than the applied force. Okay, and lastly, in case 3, you have a case where it's maintaining a constant speed. So you've got the normal force, you've got the weight, you've got the applied force, and you've got friction. And notice I drew friction less than normal force, like I have been the last few diagrams, but I drew friction the exact same length as the applied force because they're now balanced with constant speed motion. So I have weight is equal to normal force, but now that's going to be greater than the applied force, which is now equal to friction. So those two are equal, but they're greater than those two that are equal. Two equal mass cars collide in a terrible wreck. In which of these cases would the cars and passengers suffer more damage? Write a brief paragraph explaining your answer. Case 1, both cars collide at 30 meters per second in opposite directions. Case 2, car A is at rest, car B crashes head-on into car A with a speed of 60 miles per hour. Okay, so here's what's going to happen. In case 1, the two cars that are both going 30 miles per hour are going to hit each other and rebound backwards. Well, guess what? They're going to rebound at pretty much, let's assume, I know cars, they do buckle in the front and they do absorb a lot of that energy during the collision, but let's kind of pretend we're talking about two, older cars that really don't buckle very much. And we're just talking about the collision itself, not how much energy they're absorbing. So in a type of collision like that, if they're coming in, each car's coming in at 30 miles per hour, they're going to rebound at pretty close to 30 miles per hour, which means each car has a change in velocity of about 60 miles per hour because of the change in direction. Whereas in case 2, car A was at rest, car B is going to smash into it and give it that energy. So now car A is receiving that energy and is now going 60 miles per hour. Car B, on the other hand, is hitting car A at rest and decelerating to rest almost instantly with also a change of speed, right? Decelerating the 60 miles per hour. So in case one, both cars are going to change by a velocity of 60 miles per hour. This is because we were originally going 30 miles per hour, but then we will get knocked backwards going the same speed. Therefore, the change in velocity is double the original velocity. In the case to car A, in case, this is in case 2, not TO, but TWO. In case 2, car A is at rest and will gain 60 miles per hour of velocity when hit, right? And then car B is going to decelerate by that same amount, which means both cars are still experiencing a 60 mile per hour change in speed. Therefore, the damages to both cars, even though they're very different kind of crashes, are going to be comparably similar. Aroldis Chapman of the New York Yankees currently holds the world record for the fastest pitch at 105.1 miles per hour. I've been clocked throwing 30-mile-an-hour pitches. However, I could throw a ball as fast as 110 miles per hour if I wanted to. How could I accomplish this? Hint, it would involve a pickup truck and probably would not be legal on a baseball field. All right, so here's the idea. If I were in a vehicle that was moving very quickly, all right, and let's say it was going 60 to 70 miles per hour, and then I lean out the window and I throw a 30 mile per hour pitch, well, then we're talking about now I would be able to go around 110 miles per hour because it's relative addition of velocities. If I'm moving with the car at a certain speed, right, and I throw a pitch at a certain speed, right, and I'm going the same direction, they would definitely be added together. So in the next section, we're going to review a few concepts and expand upon concepts that we already introduced. Section 2.1, 2.7, and 3.4. Briefly summarize how to make a free body diagram. Say everything that is important about a free body diagram in as few words and as sentences as possible. Well, first we sketch a situation and identify any external forces acting on the system. When I say system, we're talking the object, whatever the object in question is. Then we place a dot next to the sketch. So after we've sketched the forces acting on the object, then we place a dot next to the sketch, and the dot represents that system or object. Draw the forces to represent these external forces, and we all draw those forces from the dot extending out in the direction in which they are applied. Then we label all the symbols, all the forces with the appropriate symbols and variables and subscripts as needed. For the next section, we're going to fill out and identify very specifically the different forces that we're going to be working with. First one, weight. Well, weight is also referred to as the force of gravity. Some people call it gravity for short, right? Understand that that is also the weight. There we go. The symbols would be F sub G, F sub W, or W. Any of those would be fine. And what causes it is it's an attractive force with Earth. Okay, Earth is pulling every object to the center of the Earth, and every object is pulling another object to the center of it. Okay, so there's an attraction between Earth and any object on Earth. The direction is down, but realistically, it's not necessarily just because it's down. It's down because it's pointing to the center of the Earth, which is always beneath our feet, since Earth is a sphere. The equation for it is weight equals mg. The next one is normal force. We can write this as a variable as F sub n or just little n. It's a force applied from a surface onto an object, but it has to be a perpendicular surface force applied onto an object. The direction is always going to be from the surface, but perpendicular. No equation needed for that. No special equation that is needed for that one. Tension. We can label tension with either F sub T or just capital T. What causes it would be the tightness in a rope, a cable, a string, a wire, a chain, and it's the force that pulls along. It always pulls in the direction along the rope away from the mass. And there's no special equation needed for that one. Well, the next one is static friction. The variable that is F sub S, little f sub S, it is caused by the adhesion between two surfaces, but two surfaces that are not moving relative to each other, the static friction. Now, the direction, it's not just parallel to motion. A more specific answer would be it's anti-parallel to motion, meaning it is always drawn opposite to the way we're trying to move. So if I'm trying to push a box to the right, static friction acts to the left. The equation, if you recall, is F sub S is less than or equal to mu times normal force. However, most times we're just going to write it as friction is fun. Kinetic friction will be written as little f sub k. That, of course, is caused by the adhesion between two surfaces where the object and the surface are now moving relative to each other. And again, it's drawn anti-parallel to motion. That means against motion. Now, this is, again, one way to write it, but that would be if you're using big F sub little f as the force of friction. I prefer to write it as friction is fun. Little f equals mu times normal force. The next one is a spring force, which is labeled as F sub S, and it is involving the stretching or compressing of a spring. So the force to stretch or compress a spring is called a spring force, and the direction is always going to be in the direction of the stretch or compress. So if we pull a spring farther apart, the spring force is in the direction of the pull. If we compress a spring, it's in the direction of the compress. And the equation we use for that is F sub S, the spring force, is equal to K times X, where K, we will learn a little bit later on down the road, is called the spring constant. The spring constant is a constant, as the name would suggest, and it is a number that tells you how stiff the spring is. The stiffer the spring, the harder it is to stretch or compress. So if K is very large, it is really hard to stretch or compress that spring. If K is very small, it's very easy to stretch or compress a spring. Think of a slinky. A slinky is a spring that if you pull it just barely hard enough, you can pull it and destroy it. It won't be able to compress back to its normal equilibrium length. Therefore, the spring constant for a slinky is very, very low. Lastly, we have an applied force. An applied force is a contact push or pull on an object. It is labeled with a capital letter F, and it's always in the direction of that push or pull, and there's no special equation needed for it. Think of an applied force as any time you actually touch something to push or pull it. So if you're, pushing a stroller or pushing a shopping cart, you're pushing it forward, you're touching the object to apply the force. Section 2.2, adding and measuring forces. What object measures force? Well, we're going to use these in class to measure forces, and they're called spring scales. And the way they work is using the concept of a spring force. The amount of spring force that you pull is balancing the weight, or not necessarily the weight, but the force that you're trying to pull it. So the force on the spring usually balances the force you're trying to measure. Whether that force is, sometimes that force will be friction, sometimes it'll be weight. It's going to vary according to how we need to use it. But a spring scale is a great way to measure forces. How many objects are required for a force to occur? At least two. And this is because forces do not reside in individual objects. Forces are the interaction between at least two objects. What two objects are involved in causing your weight? Well, that would be you and the Earth. Okay, the weight, your weight, is the Earth's gravitational attraction to you. Okay, that's how much you weigh. What two objects are involved when you walk? Well, when you walk, it is your weight stepping down on the ground, but it's also the normal force pushing up from the ground, and what prevents your foot from sliding and skidding on the ground every time you take a step would be static friction in the direction you walk. So when you walk, static friction actually acts forward to prevent your foot from sliding backward. Section 2.3 and 2.4. What quantity has the same direction as force? What does force actually do? Write a brief paragraph to explain your answers to these questions. Acceleration is always in the same direction as a net force. Forces create push or pulls on objects, and forces are interaction between two or more objects. Now, let's take a look at this test your understanding. We have a free body diagram right here. The situation is an elevator that has two forces acting on it. The weight of the elevator pulling down towards the center of the Earth, and the tension force pulling up along the cable away from the elevator. Tension always goes up in this situation, weight always goes down. What's going to be different about these forces is how they compare to each other. When are those forces equal? When is one force greater than another force? Here's what we're going to do. I'm going to do a couple, and then I want you to then pause the video and try and answer the remaining scenarios and see if you can figure out the relationship between tension and weight. Okay? And then resume the video to see how you did. Let's start with the first scenario. The elevator is at rest. Well, when the elevator is at rest, forces are balanced, because rest means constant velocity of 0. And if forces are balanced, that means forces up equal forces down. That means tension going up equals weight going down. So when the elevator is at rest, those two forces balance each other. The elevator is moving up with a constant speed. Well, constant speed is a similar situation of at rest. Constant velocity means forces are balanced. And again, if forces are balanced, forces going up equal forces going down, which means, again, tension equals weight. We'll call this letter A, B, C, D, E, F, and G. Right now, let's jump over to letter D. We'll do one more together, and then I want you to pause the video and try to do some of these other ones and test yourself and see how you do. Okay, resume the video to see and check. Letter D. The elevator is moving upward and speeding up. Okay. Now in this situation, if it's moving upward, the velocity is up But if it's speeding up, the acceleration also has to be up. And according to Newton's second law, net force equals ma, the direction of acceleration is the direction of the net force. They point the same way. So the net force also has to be up. Well, if the net force is up, that means the force that is going up has to be greater than the force going down, which means we would draw the tension longer than we would the weight. And therefore, tension is greater than the weight. Okay? So again, we just want to consider comparing tension and weight. Are they equal? When are they unequal? If they are unequal, how are they unequal? Pause the video and try C, E, F, and G. Then resume the video to see how you did. Okay, let's take a look at letter C. The elevator is moving downward with constant speed. Well, here's the catch. Constant speed. I don't really care which way it's going. If it says constant speed, then forces are balanced. That's Newton's first law, which means forces going up equal forces going down, which means tension equals weight, just like A and B. Letter E. The elevator is moving upward and slowing down. So here's our force diagram. It's moving upward, but it's slowing down. So velocity and acceleration have to go opposite directions. So if it's moving upward, the velocity's up, but if it's slowing down, acceleration must be going down and moving opposite direction. If acceleration is going down, net force is going down. And if the net force is going down, that means the downward force, weight, must be longer than the upward tension, which means tension is less than weight. Letter F. The elevator is moving downward and speeding up. Okay, so we're moving downward, velocity is down. Speeding up, acceleration must go the same way, so acceleration is also down. Net force goes the same way as acceleration according to Newton's second law, and which force is pointing down to give a net force going down? Weight. The weight must again be greater than tension, therefore tension is less than weight. Number 9. The elevator is moving down and slowing down. So velocity's down, but if it's slowing down, acceleration has to oppose that and go up. And if acceleration is going up, net force is going up. If net force is going up, that means the upward of the two forces, tension, has to be greater than the downward force of weight. And therefore, if we're moving downward and slowing down, tension going upward is greater than weight going downward. Section 2.5, Inertial Reference Frames and Newton's First Law. Again, this is a review. State Newton's first law. What type of motion does it have if all the forces on it are balanced? Well, again, Newton's first law states that objects will continue to move with constant velocity when the net force acting on it is zero. And if the net force is zero, this means the forces acting on it in opposite directions are going to be balanced. Is it possible for an object to move horizontally but only have vertical forces acting on it? Give an example. Yes, this is possible. Think about the Newton's first law lab. You had a rolling ball that moved horizontally through two photo gates. A ball could be rolling with a constant speed on a horizontal surface. This means the ball has a force of gravity acting downward and a normal force pushing upward from the surface, yet it does not contain horizontal forces. We're still moving, but without horizontal forces. Only vertical ones. Section 2.6, Newton's second law. What does mass measure? Mass measures the amount of matter. that an object contains. For all intents and purposes, mass is how big an object is. It measures in kilograms. Newton's second law states that a net force causes a mass to accelerate, and we can write that as sigma F equals ma. Please note that you can write sigma F, the net force, as causing force minus opposing force. We're going to be writing it like this most often. Causing force points in the direction of acceleration. Opposing force points opposite to the acceleration. Section 2.8, we're going to take a look at this example with the car, and we'll take a look at this example with the acceleration time graph in class. Thank you for following along with me. I hope you found this helpful. Please remember to write any question marks next to notes that don't make a whole lot of sense at this point. Thank you.